So we're going to go over these slides in the second hour. It's actually, some of them are a repetition of what I just told you in the first hour. Let me get the chat disappeared. Let me get the chat back on. All right. And yeah, I don't need the participants information here. I can put myself. It's not like this. So, all right. Okay, so and I'm going to also show you some nice sites that provide really nice computer graphics applications. So what is computer graphics? There are many definitions. Any use of computers to create and manipulate images. By the way, let me just start this one. When this one starts, you cannot see me. Can I put this on top as well? No. Oh, I think I'll be able to do that. What about this? Can I still? No. I'm just going to either. I think I can just start sharing my video when I'm doing PowerPoint slides. Let me close this one and let me turn on my camera via WebEx. Where is it? Oh, right here. Yeah, start video. Yeah, the reason I was not using WebEx's camera is immediately clear. As you can see, my video image in this version is extremely small. But yeah, anyway, it's better than nothing. So let me just start. Yeah, now I'm floating. It has some video settings. Does it have any size? Resolution? Only 360. No. Yeah, it's just going to be small like this. All right, so I hope you can see the slides in full screen and also see a small version of me. So computer graphics is any use of computers to create and manipulate images. In this regard, I didn't mention the difference between image processing and computer vision and computer graphics. So in computer graphics, the problem that we're trying to solve, we are manipulating images. Actually, it says manipulate images, but it doesn't get the image as input. In computer graphics, the direction, let me also use annotate. So the direction of generating these images is from a virtual world. So we have a three-dimensional virtual world, like those trees and houses. Okay, so we have a 3D world, and in computer graphics, we generate a photograph of this 3D virtual world. In image processing or computer vision, the problem is to take real photographs, real images as input and make inferences about the 3D world, the real 3D world these images are taken in. So that's what computer vision is. For example, in robotics, computer vision is used a lot because in order for robots to see, they have cameras. So in anything that processes the images of real world images and try to extract some 3D information about those 2D images, like, are there any obstacles in front of me? Who is this person I'm speaking to? Like face recognition. All these applications are computer vision applications. So computer vision in that regard is solving a different reverse problem. So it's a completely different area in which the directions are reversed. In computer vision, we have the 2D images as input, and we try to extract some 3D information like depth or recognition of certain objects, some inference about a real 3D scene. So that's what computer vision is. We have a real 3D scene, and we make inferences about that 3D real scene by using the images as input. In computer graphics, on the other hand, we have a virtual world, and we generate 2D images of these, we take photographs of these 3D virtual world in computer graphics. There are certain areas in which techniques from both areas are mingled together. They are used together, like augmented reality. Augmented reality is the area in which real life imagery, our real life vision, real world vision is augmented with computer generated imagery. So that's what augmented reality is. So in order to, one part, it has the computer generated imagery. That's where computer graphics takes a part in. The other part, since we have real world images, those real life objects and computer generated objects have to interact together in this, in front of us in this partly virtual, partly real scene. And therefore, in such applications, both computer vision and computer graphics are used together. But we are going to focus on computer graphics in this course, in which we are going to, let me stop annotating. We are going to focus on generating 2D images. All right. Now, the tools and algorithms used to make such pictures, computer graphics algorithms, computer graphics sometimes may also mean that, all the software, hardware, the computer graphics has become so developed in the latest years, mostly due to the fact that the developments in the hardware is really huge, that the GPUs, graphics processors units, what we didn't have 20 years ago in $1 million high-end workstations, you can have it on your desktop in your home. Okay, so the GPUs are really good developments in terms of developments in hardware, made it possible to have these high quality images that we see these days. And Perlin is an important personality in computer graphics, and this is what his definition. What you need to show other people your dreams. So the fact that we're getting pictures of our virtual worlds mean that that world that you're taking picture of, there is no bound to it. It's bounded only by your imagination. That virtual world, for example, may be non-Euclidean world in which the objects may have different geometrical properties. The colors, the lights may be different than what we have in our own world. Okay, it may have 3 suns. You may envision a world with 3 suns with different colors, and try to see how the pine tree in that virtual world is going to look like. So really, whatever you can dream about, it's really, so the modeling part and designing these scenes really requires lots of artistry, and therefore computer graphics is like an interdisciplinary field. Not graphics algorithms itself, computer scientists contribute there, but designing those virtual worlds, you can imagine there is lots of artists. They should have some artists in you in order to design these nice looking virtual worlds. There's also in games, for example, there's the sound component, there is human-computer interaction component, in addition to these computer graphics algorithms. So all these modelers, they are really, artists basically do these models in those nice looking games. And here our definition in this course will be, there will be some math, there will be some simple physics of interaction with light interacting with materials, or bouncing of surfaces, very simple physics, very simple math, and some coding and tears and fun. So I hope not too many tears this semester. I mean, tears usually when you're doing the assignments, students are complaining about the assignments being difficult. Yeah, maybe I think I would like to interpret this as tears of joy, because the first time you see your code working and generating those images, it's really happiness. Yeah, nothing than happiness. This is not, yeah, if you approach this course as a not difficult course, it's not a difficult course. There's not too much material in this course. We have compared similar courses in United States. They teach lots of other things like physically based models, or these, I mean, there are like elastic surfaces, some more complicated graphics, the more like liquid. How can you model liquids, fluids, and how can you have and animate them? They probably require much more difficult mathematics. We're not going to cover those here. Our mathematics in this course, this is like an introduction to computer graphics, which we will see just the basic algorithms in their most basic settings. Yeah, lots of small spheres in ray tracing. Yeah, assignments. I don't think assignments are difficult. You may. I mean, yeah, it may be open to discussion. Some of them. I mean, because you're busy with other things. That's we also know that you have other courses. You have technical electives. You have graduation project courses. But still, the amount of work that is required in this course, I mean, we reduced the number of assignments from 4 to 3 in all of the previous years. Again, we just fixed it at 3 assignments at the beginning of the semester. So these 3 assignments, some code, part of the code, we are going to provide it to you as templates. So you will have some code to build upon. The main difficulty, I think, will come in the last assignment where you'll need to code in OpenGL, which may be very difficult if, I mean, you're not familiar. The difficulty may be the thing that we see in theory in class, how it relates to pieces of code in that library, but we will try to ease this transition by providing lots of examples. Okay, and in OpenGL, there will not be spheres. It's really interesting, a sphere becoming the very simple object in ray tracing. We will be using spheres a lot in ray tracing, but in OpenGL, there is no function that says draw sphere. Okay, there's no drawing sphere function. You have to have your own sphere function by either composing it from triangles or quads on your own. So there we will not have, we will provide all those scenes to you. You will not do modeling in this course. We will provide the input scenes to you, and you will, your main purpose will be to render. Rendering is the process of getting that virtual scene information and producing that to the image. This is the code we will be writing is for rendering only. There are 3 main subfields in computer graphics: modeling, rendering, and animation. So we will be focusing, as I said, the second part. We are not going to be doing modeling in this course nor animation. We have a computer animation course which I offered once or twice quite some time ago. So there's a graduate level animation course which deals with like kinematics, inverse kinematics, forward kinematics. So there are different, how do you generate animation? There are different ways to represent rotations. But we're not going to focus on those here, just rendering. All right, let's continue. Yeah, here's cow. So it's like cow is our department's official mascot, right? So our website for the bulletin board website is called COW, Computer Engineering on the Web. That's an acronym, but yeah, it will not be. This is what's. If we are going to show you a model, we will start with a cow model, not with a bunny or a teapot. So, but we don't. I don't know why I didn't put a cow in that horse and mug. Yeah, maybe this year we are going to generate it with a cow and mug, or maybe cow and a cappuccino cup. Since I just downloaded a cappuccino model, so. There are many modeling techniques, polygonal models. These models can be generated by hand by using those tools like Blender or Maya or 3D Studio Max. Sometimes there are 3-dimensional scanners that gives you point clouds. And there are many issues. For example, how can you, if this model contains many triangles or quads, how can you simplify those? How can you simplify this object to have a lesser number of triangles, lesser number of quads? This is especially useful when you're viewing this cow, for example, from a distance. If this cow is very far away, there is no use to render all those 10,000 quads. If it's very far away, maybe with just 100 quads, it will still resemble a cow, and it will you will not be able to distinguish with the detailed version. This is called different of levels of detail modeling. There are 3D scanner-based modeling, polygonal models. There are procedural models, random models, like generating the mountainous terrain with some random functions. I'm going to show you examples on those. And Blender is a popular open source modeling program. And rendering is the process of generating the 2D image from a scene definition file. The scene definition file I just showed you maybe not contained the horse model. If you remember the horse model, there were coordinates of vertices, and it had which vertices make up which triangles, the triplets of vertices. So it didn't have a structured format. You need to know the format in order to be able to parse that file. There are more structured scene formats based on XML, which give you, for example, this is a scene. The scene is composed of these shapes. This is a material. The material properties are these. This is an object with this geometry and this material. You can have more structured formatting of these scene files, and there are some scene formats are Blender format, FBX format, or these OBJ format are some common formats. And similar to modeling, for rendering, there are also different techniques. There's ray casting, ray tracing, image-based rendering, volumetric rendering, forward rendering pipeline. We'll see ray casting and forward rendering pipeline in this course. We're not going to see these other rendering techniques like radiosity. Radiosity is a technique which generates really high quality images, but it's really computationally very expensive. Volumetric rendering, image-based rendering, and it's used also in animations. So here's a small video. By the way, these slides are... Oops, it's too loud. Can you hear me now? Yep, okay. Yeah, probably when the could you hear the music? Maybe there was no reason to share the music with you. It's just the background music. Anyway, so let me continue this. So is this the same? Yeah, look at this. Look at the scene in which we see a shoreline. So look, it was really highly detailed. So you can find similar examples in different places. So let me just mute it. And how detailed the modeling is. It's really, computer graphics has come to, I mean, in this course we're not going to be generating images that are like these, but this just shows you where computer graphics, what computer graphics is capable of. Look at this image. This image looks like a real photograph. Probably it's a, look at the light sources. All these light sources on the ceiling and these ones, they contribute the light in this room. The modeling and the reflections, there are some reflections that we see. It's really highly detailed. It looks really like a real world photograph. And the goal is to generate these photorealistic images, and sometimes it requires lots of computing power, lots of GPUs. And this is a photo from Lucasfilm rendering farm, especially when they're producing those CGI movies. They need to generate really high quality images. Being real time is not the main purpose in non-interactive movies. When you're having a movie, if you can spend 1 hour to generate a single frame, and you can dedicate lots of renderers like this. This is called a rendering farm to generate those 1 frame per hour in this detail. So things that are of concern in computer graphics is first to increase the quality of the images that are generated and to do it as fast as possible. Why do we want to do it as fast as possible? Because you don't want to play a computer game in which the frame rate is 3 frames per second. It will not appear as smooth. It will be very irritating to play that game. So if you want real-time interaction, we want at least 25-30 frames per second generated. And there's a compromise between these two. If you want to generate this level high quality image, it takes time. Okay, so you need to it takes lots of computational resources. Probably this image may have taken an hour or 2 hours or maybe a day to generate at this quality. But if you want interaction, you don't want to wait 1 frame per day. So in that sense, some games, they allow you to, for example, reduce the detail in the games, reduce the number of lights, reduce, for example, effects like detailed shadows, the dynamic textures, use low quality textures. So all these different parameters may make your rendering process, changing them affects the speed of your rendering process. The goal, so this
Hocam,
is, yes.
can I ask a question?
Yeah, sure.
Like,
Please.
I saw a video on internet, like, it was a like seashore view, but when from the top, and when it gets closer, it actually kind of gets in a loop. Same like view.
Okay, I see.
Actually, yes, loops. Is it also like this
Yeah,
a trick of computer
yeah,
graphics?
maybe it may be. Yes, yeah, it's like making certain things random to make them look as natural as possible is one thing people do. But sometimes we make repetitions. For example, there's a shoreline that you've seen, it may be, or a big texture like a huge grassland. But if you get close, you may see that, oh, okay, these grasses are actually a repetition of the same thing. So that's another trick we use a lot to repeat a certain object in different places. Trees duplicated in different places, because in real life these duplications do not exist, but in computer graphics this is done a lot to just repeat or put them in a loop. If there's an animation, for example, put the animation in a loop. But the good thing is, I mean, if it's a good animation, if it's possible to put some randomization in the animation that will make it appear as realistic as possible. Okay, so this is what these are, again, some tricks. Lots of the things in computer graphics are small, these nice tricks that appear as real. In order to make it appear as real, our goal is just basically to fool human vision, to see that what the human is seeing there is real. There's a huge application in virtual reality as well. When you put on those virtual reality goggles, you're seeing a virtual environment, and seeing in stereo increases the presence a lot. So stereo vision makes us perceive depth, and that's another trick we use to feel that the person is really present in that environment. Yeah, thanks for the comments.
We have some new stock Windows pixels and other programs like 3ds Max, Maya.
Let me just show you some snapshots from here. Look at this cave. Okay, so the lighting, the shadows, I mean, it makes this really like a photograph, but it's a real-time generated. It's from, I think it's a snapshot from it's a movie from a game, a demo from a game. but it looks really real. Look at this. Yeah.
And body position to look more natural. For the character to more realistically interact with the environment, we've added the ability to trigger seamless contextual animation events, like her hand on the door.
That's promising.
So if you look at this, I mean, the person's walking is still not that human. You can see that it's a computer game. But these are other things. How do you do motion capture and map those motion to these models to make animation more realistic? So all these things are actually, we are not going to focus on animation, but there, as you can see, there are lots of applications of computer graphics. There are other goals like computer-aided design or computer-aided mechanics. You design parts before you manufacture them. You can do stress tests. You can actually test the material properties under different stress conditions different heat at different temperature. And you can, architects may design buildings on computer before they again construct them. So it's, in other words, computer graphics provide you a way to prototype. So this is a way to prototype before you actually go to manufacturing. Because why do we need prototypes? Because they're less costly. So that's another thing we have in computer graphics. It allows you to prototype in different fields like architecture, mechanical engineering, and there are also other goals. We don't always have photorealistic rendering. There are also non-photorealistic images like this one, like the cartoonish edges, the contours of the objects are more visible. The reason for that is to have a cartoonish feeling, because we as human beings, we love art, we love cartoons, and we're already seeing the real world with our own eyes. Why aim for photorealistic images too? I want something, since this is a virtual world, I want to see a virtual world in a non-photorealistic manner, because this way of artistry is what maybe people make happy. I mean, we enjoy these non-photorealistic images as well. So Yorum shared some link with us. Let me just also continue to this one. Yeah, and so this is a really nice meme. So in 1996, it was like this. The polygons were visible, the animation, the joints, they were going in, I mean, look at the joints, they were really visible. And this is 2000, this is probably still an artistic drawing. I don't think this is a computer generated. This is not from the game itself. It's really like a two-dimensional. Or maybe if it's really from, I mean, if it's from the game, then the game applies some non-photorealistic rendering techniques to make it look cartoonish. Okay, but that's also good. There's some people may prefer some artistry, and there's the video we have seen is probably even better than this one, because the backgrounds, as you can see, it's a two-dimensional drawing. But as I said, even in a two-dimensional, if it appears like a two-dimensional drawing, but it's actually a 3D virtual world and you play in it in real time, that also is something enjoyable. As I said, sometimes playability, interaction, or appearing non-photorealistic even is not a bad thing. And there are better versions of this in 2021, as you can see. But yeah, as I said, the only purpose is not always getting photorealistic images. Depending on the application, there are different goals. Let me continue on this quickly. We have like 10 minutes left, and I want to finish the first set of slides today. But it's just a general discussion on different applications. I mentioned about the virtual reality and augmented reality. I'm going to skip those. And extensively used for games. So computer graphics is like these days is equal to games. And there's a game engine for that, which is Unity. It's very popular. Unity game engine is very popular. You don't need to know advanced computer graphics algorithms to start creating your own games in 1 hour or so, 1 hour or two. And these days, Unity is used for like producing also hyper casual games, which are like very fast, cartoonish looking games, not like the ones that you see here. I mean, generating content, designing worlds is really difficult. I mean, look at this ship that you see here. I mean, it takes a lot of man hours to build a ship that is in this detail, to design a
Hocam,
world. Yes.
they are already like ready models
Oh,
that
yeah,
you
yeah,
can buy
exactly.
for
There are
Unity
assets.
project.
Exactly. There are assets in the Unity asset store. You can buy actually you can buy assets that are designed for a whole different genre of worlds. For example, if you want a medieval coastal city, probably there are assets for that. Yeah, you're perfectly right. I mean, this is all Unity also makes it very easy to import artistry from models from different people, and you pay for it for if you're getting these high detailed nice assets. And I think Unity made it really easy for content creation, so they're really good, but if you want to have a game, for example, which doesn't look like any other game with different lighting, rendering, still knowing the mathematical background, this theoretical information about how we get this image in the first place on our screen. I mean, knowing the technical background, it will allow you to make modifications to what you see on the screen. Okay, it will not be limited by what Unity provides you, because you can also have your own shaders in Unity, but how do you write a shader in Unity? In order to do that, you have to know the theory behind it. Okay, so yeah, they're choosing movies, visual effects, computer-aided design, computer-aided mechanics. It's used in simulation and training extensively, scientific visualization. Yeah, and we will be focusing on 3D graphics in this course. The coordinate system that you see here on the screen is a left-handed coordinate system. And the reason I tell you this left-handed is that because in right-handed coordinate system, this z-axis is towards us. If x is to the right and y is to the top, z should point towards us in the right hand coordinate system, but there's a transformation from right hand to left hand because we may sometimes want the z coordinate to indicate the depth of objects from us, how far the object from the camera. And we will usually have our image plane parallel to the xy plane, or sometimes exactly on the xy plane. So we will define an image plane. We will define an image window on that image plane. So we will talk about planes, vectors going off planes. So this is the geometry and mathematics that we will be talking about in the following weeks. And we are going to focus on 3D. Still, there are 2D graphics examples, but we will be focusing on 3D graphics in this class. And rendering, I told you already that we will focus on rendering. And here is a figure that shows the main process, the overall pipeline. This is called a pipeline because starting with the virtual world, we will we will basically run a sequence of procedures. We will just follow certain procedures step by step in some order until we get the image at the end. The image itself may be a continuous light field, but we will discretize it to pixels. There may be the geometry, materials, dynamics applied to that first. There's lighting, the camera, viewpoint. We will focus on rendering part. The images, actually the images here, the images then is input to our hardware display. Then the display produces this light field which we can see with our own eyes. So here there are the output is perceived by an observer human, which then interacts with the system. We will talk about display devices on Thursday. So perception, vision, display devices a little bit. But this will just be, again, like background information. We will not use this information about hardware or our vision in the rest of the course, just to show you that the hardware is also important. What we see is important. We are going to talk about display devices and images and video. So this is in the first weeks, I think on Thursday, I'm just going to go over images and display, and that will be it. Our main focus in this course will be on this rendering part of this system. Yeah, this geometry, materials, rendering will be the main thing. And I don't think we'll have some, usually we leave this animation to the last week of classes. We just talk briefly about what problems are there in animation. We'll briefly touch upon animation in the final week. So the most of the course is going to be this green part, rendering, how we model the scene. We are going to see different scene representation formats, how we can model materials and the interaction of light with material, and different cameras, different projections like perspective projection, orthographic projection, and how we can use these different parameters to finally render a single image. And this is our book. You're going to put this book on AutoClass in PDF format. You're going to have access to that. It should be available in the bookstore. If not, we'll see. We'll order it, but I think it will not. They will not be able to acquire it for this semester. We should have ordered some already. There should be, if you want hard copy, you should be able to get, but a soft copy, we are going to provide it for you on the class. And we have a course website here, which is also on the course syllabus, and we will be mainly using AutoClass. We will have a single section. All sections, both section 1 and section 2, are going to be merged into one lecture, and all the announcements, the exams, when they're online, they're going to be there. One midterm, one final exam. We plan to have the midterm and final exams online, and we are going to have some face-to-face activity as well. I mean, before the midterms and finals, for example, I may have some question and answer session face-to-face in BNB1. And you're also always welcome to visit me in my office by scheduling an appointment. So we are open to face-to-face meetings as well. Although the exams and the course conduct is going to be online, I will have these face-to-face sessions. We will have 3 programming assignments, and this is the syllabus, and that's it. I think we still have some time. I want to show you some websites related to computer graphics. One of the yes, yeah. If you have any questions,
can I ask a question about the
sure.
conduct of the course?
Yes.
Like last year, we had 1 day a week lectures. What about this year?
Oh, 1 day
Are
a
we
week?
going to have?
Actually,
Yeah,
last year it was 2 days per week. I mean, it wasn't 1 day. It was
but we had classes just 1 day, like with Hoca.
Oh no, with me it wasn't like that. I was having
Okay.
2 different days, two plus 1. So I will be conducting the same way. So Tuesdays and Thursdays. It will not be.
Okay, thank you.
Yeah, it will be 2 hours today. I mean 2 hours on Tuesdays and 1 hour on Thursdays at 11:40. So yeah, we will have asynchronous lectures like this, and I will put them on YouTube. I will provide the link on AutoClass. So one website that I like is, which just implements what we are going to learn. In addition to C, we are going to learn a new language named the shader language in GLSL, GL shader language, which allow you to generate graphics. By the way, this is real time. This is not a movie. What you see here on the screen is currently running on my computer's GPU. For example, these ones too. Okay, there was one. Let me just search my email. There's one demo that I like particularly. I think it's Yeah, this is most advanced fragment shader I have seen. Look at this. You see the terrain, right? Like maybe you can actually view it in full screen. So it's the frame rate is a little bit off, but the image that you see here is real time. It's interactive. Actually, there are some keyboard or mouse interaction. Yeah, actually, I can click on my. Look at this. I'm currently clicking on, and maybe clicking on the left mouse button starts it again. I'm not sure, but can I slow down or so I go over the mountain? There should be some keyboard mappings too. I'm not sure how they work. We should look at the code. But the code that generates this flyover, this mountainous terrain, is this code. Actually, there are, I think, the one in the buffer. So this main image code is really small. There is, I think, this one. Yeah, this is the code that generates this. Look at it. Okay. So what does it do? There are some velocity vectors. This is the main image. So it looks very much like the C code. I mean the function definitions, but there are certain modifiers or certain types like this vec4, vec3, which we don't have by default in C. But in this GLSL language, vectors are just like integers and floats. They are the they're citizens of this language. So the camera path, but everything is like with math and with these equations that you see here. This is the lighting, the ambient, diffuse, specular components. This is the color that you see here. For example, let me remove diffuse lighting. Let's see what will happen. Let me compile it again. Oh, so diff undeclared identifier. Let me just do this. Diff, I'm just going to make this 0, 0. Wow, this is a two-dimensional vector? Let me see. Oh, this is the dot product of two vectors. Oh, this is a single vector. Okay, I need to say this. Oh, this is a dot product, so I can just say 0. Okay, let's see what will happen. You see what happened? It became much darker. So I just changed a piece of code here. Now I got the light back, the diffuse light. So you can, this is really, what does happen is that the diffuse light we had here, let me just turn it off again. It became a darker scene now, maybe just the ambient color. So it became a completely different video by just changing a single line. And what does this do? There's some light and there's some normal vector. The dot product between two vectors determine how much of light is reflected from that part of the terrain. And this light is nothing but a three-dimensional vector. This is another three-dimensional vector. And we are going to see how this, I mean, the normal is computed, the normal at the surface. But yeah, look at this. It's not a very long code, but yeah, it's still lots of mathematics involved. But it's one of the most advanced shaders that I have seen. But it's really remarkable. This is what is going on real time by executing C code on the fly on my GPU. Okay, very high detailed terrain. So just you may take a look at this shader toy. There are many better examples and nice examples similar to this one that I showed you. And this is the second part of the course. We will also learn that language, the GLSL language, but we will write really not advanced shaders like this, much simpler fragment shaders by using this language. Okay, so I will be happy to answer if you have any questions. I will be happy to answer them. But otherwise, that's it for today. If you have any questions, feel also free to send me an email. I hope. Yeah. Oh yeah, I will ask also just that. Yeah, we should share the slides. Yeah, I will ask Ozoje about this because he prepared the slides. We will probably, I think it will be okay for us to share them in PDF format, or maybe if okay, we may also share them with PowerPoint. I will ask Ozoje about this, and we will share the slides beforehand, before the lectures. Okay, I took a note of that.
Are the exams online or face-to-face?
They will be online. The exams will be online. The way we did that last year, we will follow a similar approach. Everybody is going to get a random question. Every student, we prepare for a single student. We prepare like 300 different versions of the same question by randomizing certain aspects, and every student is going to get, for example, there will be like 20 questions or 15 questions, and each of those 15 questions will be randomized, and students are going to work on them individually. Obviously, we don't want you to cheat. Last year, we didn't even turn the cameras on. Probably there was some cheating. We cannot avoid that. But if we have the cameras on or not this semester, we are going to discuss with Ozoja about this. By the way, let me stop the recording at this point.